Thank you for watching my videos all these years and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the previous year questions from the section Analysis that have appeared in the CSIR National Eligibility Test. In this video, we discuss 4 questions, question number 4 to 7. These questions are suitable for all these examinations. Right. This is the question that appeared in 2013 June, and the problem is on the number of functions. The given question is, consider two sets. A is equal to the set consisting of 1, 2, 3, and B is the set consisting of 1, 2, 3, 4, 5. Choose the correct statements. We are given 4 options. Option 1. The total number of functions from A to B is 125. Option 2. The total number of functions from A to B is 243. Option 3. The total number of one-to-one functions from A to B is 60. And in the option 4, it is given the one-to-one functions, the number of one-to-one functions from A to B as 120. Right. Let's now discuss the solution of the problem in detail. We are given 2 sets. A is equal to the set consisting of 1, 2, 3, and B is the set consisting of 1, 2, 3, 4, 5. So clearly, how many elements are there in A? There are 3 elements. Therefore, the order of A is 3. In B, we have 5 elements. Therefore, order of B is 5. Now, let us recall a formula for the total number of functions from A to B. So, first let us take option 1 and option 2. And let us now recall the total number of functions from the set A to set B, where A and B are both finite sets, is equal to the order of B, the order of the codomain, to the power of order of A, that is the order of the domain. So, the formula is the order of the codomain to the power of order of the domain. So, the order of the codomain is 5. The order of the domain is 3. So, 5 cube, that is 125. Thus, option 1 is true and option 2 is not true. Right. We call on options 3 and 4. It's about the one-to-one functions from A to B. Is it 60 or 120? So now again recall a formula. The total number of one-to-one functions from A to B, where A and B are finite sets, is order of B, P, order of A, number of permutations. Order of the codomain, P, order of the domain. Order of the codomain is 5. P, order of the domain is 3. 5P3, that is 5 factorial by 5 minus 3 factorial, that's the formula. 5 factorial is 120 by 5 minus 3 is 2, 2 factorial is 2, 120 by 2 is 60. Thus, option 3 is true and option 4 is not true. Thus, the answer to this question are options 1 and 3. By the by, we have come up to the level of number of functions and number of one-to-one functions. Suppose we ask for the same question, number of on-to functions. Let's say, let A and B be finite sets with M and N elements respectively. Then the number of onto maps or functions from f from a to b is given by the formula sigma k is equal to 0 to n minus 1 to the power of k into n minus k to the power of m into nck, where n less than or equal to m. Where n less than or equal to m, then only so many onto functions will come. When n greater than m, that is, the order of the codomain is greater than the order of the domain, then there are no onto functions and the number of onto functions will be 0. So, in our question, order of the codomain is 5, which is bigger than order of the domain 3. So, n greater than m. Therefore, there are no onto functions. Therefore, the number of onto functions from A 1, 2, 3 to B, the set consisting of 1, 2, 3, 4, 5 is 0 because the order of B is greater than order of A. That's it. So, that is the detailed discussion of the solution of this problem from the section real analysis, and it is related to number of functions. Let's now move to the next question. This question has appeared in 2013 June, and it is about one-to-one and onto functions. Let A be the set consisting of x square where 0 less than x less than 1, and B is the set of all x cube where 1 less than x less than 2. Which of the following statements is true? We are given 4 options. Option 1, there is a one-to-one and onto function from A to B. That means A and B, there is a bijection between A and B. Right. Option 2, there is no one-to-one onto function from A to B taking rational to rationals. Option 3, there is no one-to-one function from A to B which is onto. Option 4, there is no onto function from A to B which is one-to-one. Agreed. Let's now discuss the solution of the problem in detail. We have A is equal to the set consisting of x square where 0 less than x less than 1, and B is the set consisting of x cube where 1 less than x less than 2. Clearly, what will be A? What will be A? A is x is 0, 0 square, 2, x is 1, 1 square. That is the open interval 0 to 1. So, clearly, A is the open interval 0 to 1 and B is the open interval 1 cube comma 2 cube, that is 1 comma 8. Right. And both of them are infinite sets. Both of them are infinite sets. Now, both of them are open sets. Now, we remember what we have studied in our MSc first year class. That is, now we call on the option 1. There is one-to-one onto function from A to B. So, we remember now what we have studied in our MSc first year, saying that any two open intervals are equivalent. Here, the word equivalent means there is a bijection between these two sets. That means there is a 1-1 and onto mapping between these two sets. Remember, so it is known that any two open intervals are equivalent. This is an open interval, this is an open interval. They are equivalent. They are equivalent means there is a bijection between them. That means there is a one-to-one and onto function from A to B. So, therefore, option 1 is true. Now what is that define function f from open interval A to B, AB to open interval C to D by, you remember this, I am sure, f of x is equal to C plus D minus C by B minus A multiplied by x minus A for all x belongs to the open interval A to B. and this is a one-to-one and on-to function. You can very easily show it. Therefore, it's a bijection. So there is a one-to-one and on-to function from A to B. And not only two open intervals that matters, even if you take any two intervals, they are equivalent. Any two intervals are also equivalent. So since A and B are open intervals, they are equivalent. That means there is a bijection between them. That means there exists a one-to-one and on-to function from A to B. Thus, option 1 is true. And the remaining options are all not true, because it says there is no one-to-one, there is no one-to-one, there is no on-to, so on and so forth. So the answer to this question is option 1. That is the detailed discussion of the solution of this problem from the analysis related to one-to-one and on-to functions. We move to the next question. This is the third question. This question has appeared in 2015 June, and it's again related to one-to-one and on-to functions. The given question is let f be a function from x to x such that f of x is equal to x for all x belongs to x. Then we are given four options. Option 1, f is one-to-one and on-to. Option 2, f is one-to-one but not on-to. Option 3, f is on-to but not one-to-one. Option 4, f need not be either one-to-one or on-to. Agreed. Let's now discuss the solution of the problem in detail. We have a map f from x to x such that f of x for all x belongs is equal to x for all x belongs to x. That is, f compose f of x is equal to x for all x belongs to x. That is, f is a mapping from x to x such that f compose f is equal to I of x, identity on x. Yes, f is from x to x, f compose f is from x to x. And that is, every x is going to itself. That is identity. So f compose f is the identity function on x. Now let us recall this result. If f is a map from A to B and G is a map from B to A such that G compose f is IA, the identity map on A, then f is one-to-one. You have to remember, f is one-to-one and G is on-to. So if you apply here, f compose f is identity means f is one-to-one and f is on-to. So using this result, f is one-to-one and f is on-to. So there is a f is one-to-one and on-to. That option 1 is true. And the remaining are all not true. The answer to this question is option 1. That is the detailed discussion of this problem related to one-to-one and on-to functions. We move on to the last problem in this video, that is the fourth one. This question has appeared in 2018 June, and it is related to countable and uncountable sets. The given question is, let S be the set consisting of ordered pairs x, y such that x square plus y square is equal to 1 by n square, where n belongs to n, set of natural numbers, and either x belongs to q or y belongs to q. Which of the following is true? That's the question. So now we are given four options. Option 1, S is finite, non-empty set. Option 2, S is countable. Option 3, S is uncountable. Option 4, S is empty. Right. Let's now discuss the solution of the problem in detail. We have, yes, the set of ordered pairs x, y such that x square plus y square is equal to 1 by n square, where n is a natural number. Either x belongs to q or y belongs to q. Now we call on option 1 and option 4. Option 1, S is finite and non-empty set. Option 4, S is empty. Now let x is equal to 0. So substitute x is equal to 0. So if you substitute x is equal to 0, then y square will be equal to 1 by n square. Then y will be equal to plus or minus 1 by n, where n belongs to n. N belongs to n. So what are the ordered pairs now? Now 0 comma plus or minus 1 by n belongs to S. How many? As many as there are the natural numbers. So how many? Infinitely many, countably many. So thus S is an infinite set, is a countable, these many elements are countable. But how many? All of them we have to count. Now we will say S is an infinite set. When S is an infinite set, S is not empty and S is not finite. Therefore option 1 and option 4 are not true. We move on to the next slide for the discussion of the remaining options. We have S, the set of ordered pairs x comma y, where x square plus y square is equal to 1 by n square, where n is a natural number and either x belongs to Q or y belongs to Q. Right. So now let us look at this one, x square plus y square is equal to 1 by n square. What is this? It is a circle with the center at the origin and the radius 1 by n, where n belongs to n. So x-axis, y-axis, it is this circle, with the center at the origin and the diameter is minus 1 by n comma 0 to closed interval 1 by n to 0. So the first coordinate x will come from this diameter. That means x is a rational number and x will lie between minus 1 to 1 by n to plus 1 by n, x. And corresponding y's you can find out. Now for n belongs to n, let us call Sn as the set of all x comma y ordered pairs. X square plus y square is equal to 1 by n square. X belongs to Q or y belongs to Q. Right. So let's now concentrate on x belongs to Q. Now what will be S? Sn is this. For n belongs to n. What will be S? The union of all these Sn's, n belongs to n. That is, n is equal to 1 to infinity. Right. Now consider Sn. Sn means, these points on this circle. So the elements of Sn are the points on the circle Cn. X square plus y square is equal to 1 by n square. This is the circle. These are the points. Now for x belongs to Q and x belongs to the closed interval minus 1 by n to plus 1 by n. That means all those rational numbers on this diameter. So x is an element on this diameter, that is x belongs to Q, a rational number in this closed interval. We have two values. So x is Q, means y square will be 1 by n square minus x square. Then taking the square root, you will get plus or minus another square root of 1 by n square minus x square. Call that as y1 as under the square root of 1 by n square minus x square with plus sign, y2 with a minus sign. So corresponding to x belongs to Q intersection closed interval minus 1 to minus 1 by n to plus 1 by n, we get two values y1 and y2. Y1 is a rational number or an irrational number. You see, there is a limitations. So these y1, y2s are on the circle. Again, these y1, y2 ordinates will also lie between the interval -1 to +1 on the y-axis. Right. So this is x, this is the ordinate y1, this is ordinate y2. So corresponding to this x, we have two ordinates. And what are they? How many ordinates you will get? For each x, you will get two ordinates. And how many x's are there? As many as x belongs to q intersection in the closed interval -1 by n to +1 by n. How many? As many as there are in q. And how many these ordinates? 2 times of as many as there are the rational numbers. Right. So now, Sn is equal to the set of all ordered pairs. The first coordinate x belongs to a rational number intersection -1 by n to +1 by n on this diameter. Y will be corresponding to that x, you will get two y's. What are they? Whether they are rational numbers or irrational numbers, we are not worried, but we are only worried about how many? 2 elements. So how many these? These are -1 by n to +1 by n closed interval intersection q multiplied by 2 times of this one. And how many these? These are as many as there are in q. As many as, because q set of q rational numbers is countable. Cardinality of q. So order of Sn will be order of the first multiplied by the order of the second. The order of the first is as many as there are in q. Q is countable. The order is LF0 multiplied by 2 times of LF0. That is 2 times of LF0 square. LF0 square is LF0. So LF0. So order of Sn is LF0. Therefore, Sn is countable. Right. Now this time you pay your attention, instead of x belongs to q, you take y belongs to q. Then y will belong to -1 to +1 by n. The closed interval -1 by n to +1 by n. That means this time you are playing the game on y-axis. That is on y-axis. Then you will get two corresponding to each y belongs to q intersection -1 by n to +1 by n the closed interval. You will get two abscissae x1 and x2. In the previous case y1, y2. This is the case x1, x2. So arguing in a similar way, we get for y belongs to q and y belongs to -1 by n to +1 by n, that is on the y-axis, all those rational numbers on this. We have two values x plus or minus under the square root of 1 by n square minus y square. This type x1 and this type x2. Right. So arguing as above, we'll get order of Sn will be again countable. You will get LF0 multiplied by 2 times LF0, that is equal to LF0. Sn is countable. So thus, in any case, Sn is countable. Whether x belongs to q or x belongs to q intersection this interval, or y belongs to q and y belongs to this interval, the Sn will be countable. And for a given n, Sn is countable. But how many Sn's are there? As many as there are the natural numbers. So we are interested in S. So S is equal to union n is equal to 1 to infinity Sn. Now S is equal to union n is equal to 1 to infinity Sn is countable. Why? Each Sn is countable. What is the union? It is a countable union. The countable union of countable sets is countable. So, I'm sorry. it is the countable union of countable sets is countable, therefore S is countable. So thus call the options 2 and 3, S is countable, option 3, S is uncountable. Thus we have proved S is countable, so option 2 is true and option 3 is not true. Summarizing all these options, the answer to this question is option 2. That is the detailed discussion of the solution of this problem, which is related to countable and uncountable sets. And this fourth question that appeared in 2018 June is a good question and important question. Agreed. I am sure that you have understood the solution of this problem and 4 problems I have discussed. I am sure that you have understood the solutions of all these 4 problems. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We will meet you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.